Yes, apologies. You've got me again. As Ian said, standing in for Helen at the last minute. So if you do have any technical questions, probably best to, well, feel free to ask, but I'm not guaranteeing I can answer them. Okay, so this is, Helen asked me to present the work that she did as part of the EBAO project. She was modelling changes to the physical impact, so on waves, due to different array, energy array layouts. So I'll go through the EBAO project briefly, the theoretical modelling study that Helen did, and then the case study she did modelling at EMEC, and then briefly the conclusions and work she hopes to do next. So the aim of EBAO is to develop and combine physical and ecological modelling techniques to address issues of array design in order to minimise adverse effects or even produce benefits while not compromising power production. 4 scenarios were considered, and I believe the one that Helen was looking at here is scenario C, so an inshore site for wave and tidal. The first stage was to design a theoretical model looking at 3 different array scenarios, which I'll go through next. Initially, it was a very simple grid with parallel depth contours, subsequently with the real bathymetry around EMEC. The deepest device at 60 meters depth, and 2 sea states taken as average sea state from the scatter diagram, and a large sea state, but one that does occur with reasonable regularity, so not the rare extremes, but what would be considered a large but reasonably regular event. 5 wind scenarios to look at the effect of wind, and all the modelling was run through SWAN spectral wave model. So the 3 device scenarios were a small grid with 10 1 megawatt point absorbers, 400 metre lateral spacing, 600 metre between rows, offset between the rows, what was considered a typical early array scale commercial development. Model 2 is much larger with 50 devices, again 1 megawatt, off spacing in separations as before, so a future commercial scale array, but also still 50 devices, but something that had built-in corridors, perhaps for access or potentially for movement of animals. And so to look at what moving the array around to, for environmental considerations, how that would affect the downstream impact on the waves. The wind scenarios were following wind of 5 meters per second, 10 or 20, opposing winds and cross winds. Here you can also see the bathymetry, which is the initial setup with the parallel bathymetry, constant steepness and still until close to the shoreline. And the model for the individual devices, they were a partially transmitting barrier, and the transmission was frequency dependent. 50 meters in size, but so the power that they absorbed was dependent, or the power that they let through was dependent upon different frequencies, so designed to be representative of the device. And the outputs were taken as transects at various places behind the arrays and along the center line as well. Okay, so that was the setup. Here you can see the results, showing the percent change in significant wave height along 4 of the transects, 200 meters, 1,000 meters, 500 meters, and 10 kilometers, which I'll go through all of them in a minute. Here at the initial one at 200 meters, the influence of the devices is obvious. There's a greater impact towards the center, and clearly for scenario 1, the small array, there's a smaller impact, and you can clearly see the effect of corridors in scenario 3. So this is really near field. You can see there's a difference between just a big block array and separating that array up and putting the corridors in. Once you get a little bit further away, so a kilometre out, you can again see the difference with the corridors. It's reduced slightly, and as you increase the distance out to 5 kilometres, there is no longer any discernible difference between a big block of wave energy devices and that one that is separated into separate blocks. The summary from that theoretical model was that clearly increasing the number of devices increases the impact, so both of them with 50 devices increase the impact. And closer in the near field, putting corridors in between or gaps in between does lessen the impact, but it decreases. What I didn't show there is the results for the wind, but she found strongly that the impact decreases with a following wind or a crosswind. So with a following wind, there's regeneration of the sea state, but it increases, conversely, it increases with opposing wind, and particularly that the differences imposed by the wind field, especially once you get more than 200 meters out from the array, were dominating over the differences by the array layout. And the impacts were also higher for larger sea states. The same three scenarios were then modelled using the real bathymetry at EMEC. These were put slightly further offshore to ensure that they were in similar depth. And they were modelled for 3 hourly sea states from the EMEC hindcast for 2005. There were 3 output locations and a full grid at 10 metres depth, the central, north of the array and south of the array. There are the 3 shoreline output locations with the pink dots. And we can see the scenarios here over the timeline. Initially, it doesn't look like there's much difference between the two 50 device scenarios, but obviously a big difference to the smaller array. But if we zoom in, scenario 3 has generally smaller impacts because the shoreline is much closer than in the theoretical model. So the actual magnitude of the impacts is smaller than in the theoretical model, but there are discernible differences between scenario 3, so the spaced arrays, and scenario 2 in this one. She also produced a grid output. This corresponds to average change in theoretical mode. So this is there isn't a black line around the coast, but you can just about make out the Orkney coast from where the blue stops. It gets clearer. So this was for the small array, this is for the larger block array, and this is for the spaced array. So there are discernible differences between these two, which are, although they reduce as they get closer to the coastline, they're more significant in the real case than they were in the theoretical case. But they were still dominated by wind and wave conditions. So, in conclusion, the array layout is important for the near field effects. So if you're looking very close to the array, just behind it, changing your layout will change the effects on the waves in the near field. But as you go further out, the local wind and wave conditions become more important quite quickly than the layout of your arrays. Next stage of work here is to examine how these impacts would affect the wider physical and ecological scenarios. And there is further work going on to develop spectral wave models in this sense, how they account for devices, to try and develop best practice and improve the representation of devices moving forward. Thank you.
We do have time for a question.
I'll try.
Or even if it's a question that can be taken back to Helen for remote reply if necessary.
Yes, your transmission coefficients.
Yep.
How do you calculate them?
I believe that one's just a simple Gaussian curve around a peak, around a wave period or wave frequency that was considered peak for the location, so for EMEC location, so the kind of wave period that a developer would target. A simple Gaussian curve with optimum absorption around that, as presuming the device would be built to be close to resonance at that point.
Okay. What was the peak value for your
I'll have to look, because I don't know. It looks to me around 7 seconds, so perhaps not optimized for me. It looks to me around 7 seconds. But that, Helen helped derive that as a sort of add-in to Swan, so we went back to the source code, put that frequency dependency absorption in there, because prior to that it was just simply a partially transmitting barrier where across all frequencies a certain percentage of energy was absorbed. But to try and improve the representation of devices, we had a couple of students work on building the frequency dependent absorption into Swan to try and improve the representation of devices in spectral models.
Thank you very much. Thank you.
Okay.
Our next speaker is Reza